Hello math friends, this is AP Calculus section 2.1. Today we're going to start by talking about tangent lines and kind of review what this means. You've talked about tangent lines in other math courses before, specifically in geometry, but we've certainly found equations of tangent lines in Algebra 2 and in pre-calculus as well. The word tangent means touching. So a tangent line to a curve is a line that touches a curve, but specifically it touches a curve at exactly one point. So when we look at the two pictures that are given here, the first one is a circle with a line, and you can see that this line right here is tangent to this circle at this one point, and we usually call our point of tangency in calculus P. And in the second example, you can see that we have another curve and we have a line that is tangent to the curve, again, at that one spot, which we are going to call P. So if our goal today is to write an equation of a tangent line to a curve at a specific point, then we have to think about the information that we need to write an equation of a line. We know that we require a point and a slope to do that. So in order to write an equation for a tangent line to a curve at a specific point, we need to know the slope of the line at that exact point. If we don't know the slope, we have to approximate the slope using secant lines. And we can say that the slope of the tangent line would be the limit of the slope of the secant lines. So in our first example, we're asked to write an equation for the tangent line to the curve y equals x cubed at the point 1, 1. So before we do any work here, let's just sketch a little picture of what this looks like. So over here, I'm going to sketch a coordinate plane. And I know that the curve y equals x cubed, that's one of our parent functions. That just is going to be a standing snake. And it has a point at 0, 0. It has a point at 1, 1, a point at negative 1, negative 1, and then it's going to have a point way down at negative 2, negative 8, and a point at positive 2, positive 8. So here's a sketch of what y equals x cubed would look like. And if we're asked to write an equation of the tangent line to the curve at the point 1, 1, then our point of tangency is this point right here. And so we want to figure out what the equation of the line is that touches our curve y equals x cubed at that exact point. So something that looks approximately like that. All right, so the first thing that we're going to do is I have a little table here. Since we don't really have a way to find the slope at that exact point, we're going to have to estimate it. And so what we're going to do is we're going to pick points that are really close to that point, and then we're going to find the slope between that point and the point really close to it. And the idea is that if we get closer and closer and closer to x equals 1, then our slopes are going to get closer and closer and closer to that point of tangency. All right, so let's start with x equals 1.5. First, we're just going to build a table of values here. So I am plugging 1.5 into y equals x cubed. Again, so I'm just cubing 1.5. And when I cube 1.5, I get 3.375. Then I am going to cube 1.1. 1.1 cubed is 1.331. And then I am going to cube 1.01. 1.01 cubed is 1.030. Then I'm going to cube 0.99. 0.99 cubed is 0.970. I'm going to cube 0.9, which is 0.729. And I'm going to cube 0.5, which is 0.125. All right, so now we need to find the slopes And so basically what we're doing here is we're always finding the slope between a given point and the point 1, 1. So I have right here in the box, because our second point, and we're going to call this point P, right? That's our point of tangency right here on our graph. Our point P is always the same point, and that is 1, 1. So basically, I'm just going to start plugging ordered pairs in. So for my first ordered pair, when x is 1.5, and y is 3.375, and I plug those values in, then I would get, in my numerator, I would get 3.375 minus 1, and in my denominator, I would get 1.5 minus 1. You do the calculation, and you get a slope of 4.75. And then I'm just going to continue that process all the way down the table. So the next ordered pair, I am going to do 1.331 minus 1 over 1.1 minus 1. That's going to give me a slope of 3.31. Next, I'm going to do 1.030 minus 1 divided by 1.01 minus 1. That is going to give me a slope of 3. And if I continue down, I'm just going to go ahead and fill in the table now that you kind of understand what we're doing here. We get another slope of 3, we get a slope of 2.71, and then we get a slope of 1.75. Okay, but what we need to remember is that our point P, which is 1, 1, lies right in between that value x is 1.01 and that value x is 0.99. So since our p-value lives right in between there, and the two closest slopes that we got were both 3, I think it's fair to assume that as we get closer from both sides, to x equals 1, our slopes get closer and closer to m equals 3. And so since that's the case, that is what we're going to use as our value for slope. So now we're ready to do what the problem asked us to do, which is to write the equation of the tangent line to the curve at that point. We know that our point is 1, 1, and we know that our slope is 3. So now we just do point slope form. So we're going to do y minus y1 equals m times x minus x1. So in this case, we will have y minus 1 equals 3 times x minus 1. And when we simplify this, on this side of the equal sign, we're going to get 3x minus 3. When we add the 1 from the other side of the equal sign, we end up with y equals 3x minus 2. In our second example, we're given a story problem. A tank holds 1,000 gallons of water, which drains from the bottom of the tank in half an hour. The values in the table show the volume V of water remaining in the tank in gallons after t minutes. So obviously at 0 minutes, the tank is full at 1,000 gallons. That point's not in the table. 5 minutes later, the volume is down to 694 gallons. After 10 minutes, the volume is down to 444. So it makes sense that as more time passes, the volume of water in our tank is becoming less and less as the water is draining out. Part A says if P is the point 15, 250, so 15 minutes after the water starts draining, the volume is 250 gallons. Find the slopes of the secant lines PQ when Q is the point on the graph with T equal to 5, 10, 20, 25, and 30. So I'm going to call this point Q1, this point Q2, Q3, Q4, and Q5. That'll just make it easier when we're finding our slopes. Okay, so if we're trying to find the slopes of each of these secant lines, like the secant line that is created between Q1 and P, Q2 and P, Q3 and P, Q4 and P, and Q5 and P. We're just asked basically to calculate 5 slopes. Okay, so M1 will be the slope between Q1 and P. So my slope is going to be 694 minus 250 divided by 5 minus 15, which gives us a slope of negative 44.4. Makes sense that our slope is negative because the level of water in the tank is, or the volume of water in the tank is decreasing. So we should have a negative slope for all of our slopes. Our M2 is going to be 444 minus 250 divided by 10 minus 15, which gives us a slope of negative 38.8. Our M3, the slope between P and Q3, is going to be 250 minus 111 divided by 15 minus 20, which gives us a slope of negative 27.8. Our M4 will be the slope between P and Q4, which is 250 minus 28 divided by 15 minus 25. That slope is negative 22.2. And M5, the slope between P and Q5, will be 250 minus 0 divided by 15 minus 30, which gives us a slope of negative 16.7. All right, so this is the work for part A. Part B says, estimate the slope of the tangent line at P by averaging the slopes of two secant lines. Well, remember that P lives right between Q2 and Q3. So it makes the most sense if we're going to use the slopes of 2 points that we should use the averages of the slopes between Q2 and P and Q3 and P. So we're going to use, for part B, we're going to average these two slopes together for part B. So for part B, if we find the average of two numbers, we just add them and divide by 2, right? So our M average is going to be equal to negative 38.8 plus negative 27.8 divided by 2. So we get an average slope of negative 33.3. And then finally, part C says, use a graph of the function to estimate the slope of the line, the tangent line at P. This slope represents the rate at which the water is flowing from the tank after 15 minutes. Okay, so basically we just need to sketch a graph here of our function. And if we plot our points, we know that our time in minutes is on the x-axis, and we know that our volume in gallons is on the y-axis. And our volume up here is all the way at 1,000. And our time in minutes goes up to 30 minutes. And so if we go ahead and plot our points on this curve, after 5 minutes, I should probably add a few more marks here on my x-axis, or on my y-axis, excuse me. There we go. After 5 minutes, there's 694 gallons in the tank. After 10 minutes, 444. After 15 minutes, 250. After 20 minutes, 111. After 25 minutes, there's 28. And after 30 minutes, we're down to 0. So you can kind of see that gently sloping curve that looks a bit like exponential decay. And if we wanted to find, or if we wanted to use the graph of the function to estimate the slope of the tangent line at P, remember P is this point right here. This is our P, right? So if we were to just go ahead and draw a line that was approximately tangent to the curve at this point, it would look something like that, right? And we already kind of did this work, so I'm not going to bother. We could try to grab an ordered pair from our x-axis and our y-axis where our tangent line intersects, but we already know that our slope here of our tangent line is going to be approximately negative 33.3 because we already found that in part B. So we're just going to cheat a little and go with that as our answer for part C. But again, we could totally take this ordered pair and this ordered pair, and we could calculate a slope using those 2 points of that tangent line at P. But it's going to be pretty darn close to negative 33.3. The next thing we should talk about is instantaneous velocity. An application of the slope of a tangent line to a curve is calculating instantaneous velocity. Think about how fast you're going in your car as you drive. Your speed is not typically constant. It goes up and down as the car slows down or speeds up based on what's going on around you. We can calculate our average velocities over shorter and shorter periods of time, and those would be slopes of secant lines, right? But as we bring our 2 points closer and closer and closer together, we're finding the limit of the average velocities, and this limit becomes our instantaneous velocity. And I think that this idea is illustrated really well in these 2 pictures below. So if you look at the first picture here, we have 2 points. We have point P and we have point Q. And if we were to find the slope between these 2 points, it's not going to be the exact slope of the line at P. It's going to be the slope of the secant line connecting the points P and Q, right? And that would be an average velocity between 2 points in time P and Q. But as we start to bring Q closer and closer and closer to P, our secant line becomes shorter and shorter and shorter, right? But that slope becomes closer and closer and closer to the slope at the exact point P. So this is the relationship between average velocity and instantaneous velocity. As we bring point Q closer and closer to point P, the slope of the secant line becomes the slope of the tangent line. And this is a very big, very important idea to understand in calculus. This idea that average velocity, the limit of it, as we bring these 2 points closer together and we keep calculating slopes closer and closer and closer and closer together, that the average velocity becomes the instantaneous velocity. That the slope of the secant line, the limit of that as we bring Q closer and closer to P, becomes the instantaneous velocity or becomes the slope of the tangent line at that exact point. And we will be using this throughout the year in calculus. This is one of our big ideas that we're going to keep coming back to over and over again. So we're going to use this idea in our last example here. It says, if a rock is thrown upward on the planet Mars with a velocity of 10 meters per second, its height in meters t seconds later is given by y equals 10t minus 1.86t squared. Okay, so that function right here, this y equals, this gives us the height in meters of our rock. Part A asks us to find the average velocity over the given time intervals. So first of all, I want to remind you that for this problem, velocity is a measure of distance over time. Okay? And finding average velocities means finding slopes. Okay. All right, so the next thing that I'm going to do is I'm going to fill in the table of values here by plugging the t values into the function y equals 10t minus 1.86t squared. So this is just calculator work. Now, one thing that I wanted to show you at this point that I haven't shown you yet is the table function on your calculators. So if you go ahead and you grab your graphing calculators, if you go to y equals, and you put your function in for y1, which our function is 10t minus 1.86t squared. So 10x minus 1.86x squared. Okay, using x instead of t, not a problem. A feature that we haven't talked about yet is the table feature, but when you need to calculate a bunch of values quickly, this is a nice feature. So if we go to second level and then above your graph key is table, okay? Now you can type in any values that you want here as long as you have your settings correct. So actually we need to backtrack for a second. First we need to go to table set, which is right here above your window key. It's a second level function. So second level table set, this is your table settings, okay? And right now it's on auto, and so this is what we need to change. We need to change our independent variable, which is our x value, to ask. And all that means is that it allows us to type in any value that we want to. So I just highlighted ask and I hit enter. And so now when we go back to our table, the dependent is going to stay on auto, okay? But when we go back to our table, so second level table, now it should be empty, okay? And we get to type in the x values that we want. And what it's going to do is it's going to input those x values into our y1, our equation that we put into y1, and it's going to give us our outputs. So it's going to do the math for us, which is really quite nice. So I'm going to go ahead and just type in my x values, which are 1, 2, 1.5, 1.1, 1.01, and 1.001. And now take a moment and copy those y1 values that there are outputs into your table on your paper. So we get 8.14, 12.56, 10.815, 8.749, 8.203, and 8.146. And again, you don't have to use your calculator to do this. You could certainly, your graphing calculator or table function to do this. You could certainly have just grabbed a regular old calculator and, typed in 10 times 1 minus 1.86 times 1 squared, and then 10 times 2 minus 1.86 times 2 squared, so on and so forth, and filled in your table that way. But I think the table function is a neat feature, especially if you're trying to calculate a lot of points. It's a little bit of a time saver. All right, so now we have the data in our table that we need to do this problem. First, I want to talk about what this would look like. If we were to throw a rock up in the air on the planet Mars, the shape, mathematically speaking, the shape that the trajectory of the rock would make would be parabola shaped when we're talking about the height, right? Because the rock would rise up to a certain height, and then at some point it would reach its max height, and then it would start to fall back down, and it would continue to fall until it got back to 0, right? Now, in this case, we're only calculating t values, basically the highest t value that we calculate. This is maybe t equals 1, and this is maybe t equals 2. And again, that's a guess, okay? So this is the highest point that we're calculating right here at t equals 2 in our table. Our other values are all kind of somewhere along this little stretch right here on our parabola. And our p-value is this point right here when t equals 1, right? So this is kind of the math that we're doing. So when we talk about this idea of the secant line, the limit of the slopes of the secant lines as we bring these q's closer and closer and closer to p, the limit becoming the slope of the tangent line, that's our idea here. Our velocity of our rock, as we bring these q values closer and closer and closer to our p value, we are converging on our instantaneous velocity at point P. So there's just a little graphical representation of what's going on here. But now we just have to do some math. So for part A, they're asking us to find a whole bunch of slopes. The first one is the slope between t equals 1 and t equals 2. So basically finding the slope between the first 2 points in our table, which is just going to be 12.56 minus 8.14 divided by 2 minus 1. You grab your calculator, do the math, and you get 4.42. Our second slope is between t equals 1 and t equals 1.5 seconds. So that's going to be 10.815 minus 8.14 divided by 1.5 minus 1, which gives you a slope of 5.35. Our third one is between the first and the fourth point, actually. So 8.749 minus 8.14 divided by 1.1 minus 1 gives us a slope of 6.09. You can see our slopes are beginning to increase. That makes sense, right? Pause for a second. Let's look at our picture again. If we look at the slope here versus the slope here versus the slope here, the slopes are starting to get steeper as we get closer to P. That is what we would expect to happen. All right, so back to our slope calculations. The fourth one is 8.203 minus 8.14 over 1.01 minus 1, which gives us a slope of 6.3. And then finally, the last slope is 8.146 minus 8.14 divided by 1.001 minus 1, which gives us a slope of exactly 6. The answer to part B, hopefully, is very simple, right? Because we did all this math and we showed that as we bring this Q point right here closer and closer and closer to P, the slope between those 2 points that we calculated as we brought Q closer and closer is getting closer and closer to 6. So we say, as our T values get closer to t equals 1, our velocities, which is our slope, right, get closer to 6 meters per second. That's our units, right? Height divided by time, meters divided by seconds. So the instantaneous velocity, velocity is 6 meters per second. And that's the answer to part B.